Good morning, one and all. Today, we are going to see about the sequence impedance and sequence network of the circuits. Previously, we have seen the sequence current, sequence voltage. Now, we need to see the sequence impedance because in the fault analysis, it might be useful because we are converting the like a phasor, normal sequence current into this positive sorry phase currents into sequence currents, no, like a positive, negative, and zero sequence impedance. So zero sequence current. Similarly, we are converting the normal impedance into positive sequence impedance, negative sequence impedance, and zero sequence impedance. Sequence impedance are the impedances that are offered by the device or components for the for like the sequence components of that current. So in the power system, you are having the generator, you are having the transmission line, you are having the loads. So while analyzing, we have to note down this all the impedance, sequence impedance of the generator, sequence impedance of the transmission line, sequence impedance of the transformer, like load, like everything. We are going to note down the what is the impedance like that. So here sequence impedance are divided into positive, negative, and zero sequence impedance depends on the currents of the different sequences. What is the positive sequence impedance? The impedance offered to the flow of positive sequence currents. The impedance offered to flow of positive sequence current is known as positive sequence impedance, and it is denoted by Z plus. Next, coming to the negative sequence impedance, that is Z negative, that is equal to, that is nothing but the impedance offered by the flow of negative sequence current is known as negative sequence impedance, and that is denoted by Z negative. Next, zero sequence impedance, the impedance offered to the flow of zero sequence currents, that is known as the zero sequence impedance, that is denoted by Z0. That is Z0 or Z0. Next, sequence impedance of star connected load grounded to an impedance Zn. So we are considering sequence impedance and with the star connected load and also with the grounded to the impedance Zn. Consider a three-phase balanced load with the self impedance Zs and the neutral is grounded to the impedance Zn as shown in the figure. So the sequence impedance of past like IA is ZS and the sequence impedance of this the balanced balanced load, and sequence impedance of IB is ZS, and also sequence impedance of IC, that is C point is ZS, and having the neutral impedance as Z, that is the balanced star connected load. So while drawing any figure, you need to name the figure. Most of us, what you are doing is you're drawing the figure, but you're not mentioning what is that figure about. Many students, so you change that attitude. So whatever the not only this, not only in power system analysis, in any subject, whatever the figures you are drawing, try to not try to. You need to write the figure name in the bottom of or in the top. You just write figure, like bottom is the universally used, no? So figure that name. What is, say, for example, ballast star connected load or balanced delta connected load. Like that, you need to mention whatever the figure might be. Now we are going to derive as a Z that cost what is ZA like in the terms of impedance, we are going to derive for positive impedance, negative impedance, and zero impedance. So here we are taking the line to ground voltages VA, VB, and VC are VA is equal to ZS into IA plus Zn into In. Next, VB is equal to ZS into IB plus Zn into In. Next, VC is equal to ZS into IC plus ZN into IN. For balanced circuits, IN is equal to IA plus IB plus IC for balanced circuit. This is for balanced circuit. Substituting this IN in the equation, you will get the equation as VS equal to ZS into IA plus Zn into In. Instead of In, we need to substitute IA plus IB plus IC and multiply by Zn. So it will become Zn into IA plus Zn into IB plus Zn into IC. Now taking the common terms outside, like IA. So if you take IA outside, then ZS plus Zn plus Zn plus IB plus Zn into IC. Next, VB is equal to ZS into IB plus Zn into IA plus Zn into IB plus Zn into IC. Similarly for VB also. Now taking the common terms outside, like IB is the common term. If you take outside ZS plus Zn. So Zn into IA plus Zn plus Zn into IB plus Zn into IC. Similarly, VC is equal to ZS into IC plus Zn into IA plus Zn into IB plus Zn into IC, because we are substituting IN as IA plus IB plus IC in this previous equation. So now taking the common terms outside. So yeah, IC is the common term. So ZS plus Zn into IC plus Zn into IB plus Zn into IA. Now we can rewrite this in matrix form. That is VA, VB, VC. That is equal to, so in the matrix format, taking the common terms outside. So IA, IB, and IC are the common terms. We are taken as outside. So this equation we can rewritten in the matrix format as ZS plus Zn into Zn, Zn, Zn into ZS plus Zn into Zn. So Zn, Zn again ZS plus Zn. So this components alone will become Zn plus Zn. Rest are all components. Rest are all components becomes Zn. So now we need to convert this into compact format. That is VA, VB, and VC matrix is equal to VABC. And here also this matrix we are converting into ZABC, and this matrix we are converting into IA, IB, and IC matrix we are converting into IABC. Now converting VABC and IABC in terms of symmetrical components. This we already we derived from the previous formulation, that is VP is equal to T into VS from the previous formulation. That video also I will give in the description. You can watch. Next, IP is equal to T into IS. This also already we have seen. Now, VP and IP are the phase voltage and phase currents. Now, again, we are rewriting this T into B012. Okay, because this is then T into VS. The sequence component we are rewriting into 0, 1, and 2. So B into 0, 1, 2 is equal to ZABC into T into I 0, 1, 2, 0, 1, 2. This also, so what we are doing is this T transformation matrix we are taking as it is, and V0, 1, 2, we are converting in terms of I and Z. So we are converting into ZABC into I 0, 1, 2, 0, 1, 2. That V0, 1, 2 and I 0, 1, 2 are the symmetrical components of voltage and currents that already we know. Now we need to calculate only voltage at 0, 1, 2 that we are taking outside. So this term becomes this will becomes that this side. So T inverse into ZABC into T into I 0, 1, 2. So this and this get cancel. So we'll get as 0, 1, 2. That is ABC. We are converting into 0 sequence component. That is 0, 1, 2 into I 0, 1, 2. Again, what is this 0, 1, 2? 0, 1, 2. What we are doing is we are taking this T inverse ZABC into T as 0, 1, 2. So 0, 1, 2 is equal to T inverse of ZABC into T. So that we are converting this ABC components, we are converting into 0, positive and negative sequence components. So this 0, 1, 2 is equal to T inverse ZABC into T. Now, what is we are substituting T here. So T already we have seen in the our previous classes. So 0, 1, 2 is equal to 1 divided by 3. So T inverse nothing but 1 divided by 3 into 1, 1, 1, 1 A squared, 1 1 A squared, 1 A squared A into ZABC. ZABC already you know here, ZABC. Yeah, this is the ZABC. That matrix we are writing because that is the sequence impedance. So from this matrix, so because we rewritten this as a this matrix as ZABC, no, the same thing we are substituting over here. So ZS plus ZN, 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 ZS plus ZN, ZN, next ZN, ZN, ZS plus ZN matrix. Now this T matrix, that is nothing but 1, 1, 1, 1 A squared A, 1 A squared. Just we are multiplying this, we are getting as ZS plus 3 into ZN, 0, 0, 0. Again, here ZS, here also 0. While multiplying, you just multiply it. First you multiply this 2, and with that answer, again you multiply with this. So you'll get a 0, 0 ZS. So this we are converting into, this is nothing but 0 sequence component. This is nothing but positive sequence component. This is nothing but negative sequence component. So that is in the terms of Z0, 0, 0, 0, Z plus 0, 0, 0, Z minus. So what we are doing is Z0, 1, 2 is nothing but in this matrix we are converting to 0, positive and negative sequence component. Sequence impedance matrix of a three-phase the sequence impedance matrix of a balanced three-phase load is a diagonal matrix. That is three sequence impedance, that is Z positive, Z negative, and Z zero are the independent. That is current of each phase sequence will produce voltage drops of the same phase sequence only. That is a conclusion from this above. Next step, sequence networks of a three-phase balanced star connected load grounded through ZN. So similarly, what we are doing is sequence network of a three-phase balanced star connected load grounded to ZN. That we are going to calculate. In a balanced system, current of one sequence considered to flow in an independent network composed of the impedance to the current of that sequence only. That you already know. Next, the single phase equivalent circuit of a power system consists of a impedance to current of any one sequence, that is called sequence network. What is the sequence voltages? Sequence voltages VA naught, VA positive and VA negative is equal to ZS plus 3 into ZN. This is from the previous formulation 0, 0, 0 ZS plus 0, 0, 0 ZS into IA naught, IA positive and IA negative. So here, this is the three-phase star connected zero sequence circuit. This is the three-phase star connected zero sequence circuit with what do you call, with grounded to ZN. So the current is IN here and having the impedance ZS. This is the all zero sequence, IA naught, IB naught, IC naught. This is the A phase, B phase, and C phase. Next, the star connected zero sequence circuit as shown in the figure. That is 9. That is in the previous figure. Here, IA naught is equal to IB naught is equal to IC naught. Next, IN is equal to IA naught plus IB naught plus IC naught. Whereas this we can rewrite as terms of IA naught. So we are converting this IA naught, IB naught, IC naught in the terms of IA, that is phase A operator. So this becomes IA naught plus IA naught plus IA naught. That is nothing but 3 into IA naught. Next, the sequence networks from this equation, that is the previous equation. In the previous equation, this you multiply, you will get the VA naught is equal to just ZS plus 3 into Zn into IA naught. Next, VA positive is equal to ZS into IA positive. That is VA positive is equal to ZS into IA positive. VA negative is equal to ZS into IA negative. That is what they formulated here. This is the zero, positive, and negative sequence network of a three-phase, that is star connected balanced load. Here is the balanced load. Here from this previous equation, we just draw this like a what do you call, zero, positive, and negative sequence network. Okay, this is the zero sequence network. Zero sequence network comprises of ZS plus 3 into Zn. That is nothing but Z0. Here having the current current as IA naught. Here having the voltage as VA naught. Similarly, here positive sequence network. Positive sequence network that is Z plus equal to ZS. That is from the previous formulation, Z plus equal to ZS. So here VA positive and IA positive. That is VA positive is equal to IA positive into Z positive. So Z positive is nothing but Z, yes. So similarly, negative sequence network. Here also VA positive. Here also IA positive. Here Z minus equal to Z, yes. So VA negative is equal to IA negative into Z negative. So Z negative is equal to Z, yes. So in the three-phase star-connected zero sequence circuit as shown in the figure, the current flowing through the neutral, that is Z neutral impedance Zn is In is equal to 3 into IA naught. So from the zero sequence network shown in the this figure, this zero sequence voltage with the reference to ground, that is VA0 is equal to minus Y minus here. This is flowing like this. So minus of ZS plus 3 into Zn, because the current is flowing in this direction. So minus of ZS plus 3 into Zn into IA naught. Next, VA naught is equal to Z naught minus Z naught into IA naught. Next, Z naught. This we are converting. This we are converting. That is ZS plus 3 into Zn is nothing but Z naught, where Z naught is equal to ZS plus 3 into Zn. Therefore, the neutral impedance Zn becomes 3 Zn for the zero sequence network. So this is the noted point. The neutral impedance Zn becomes 3 into Zn for zero sequence network. Next, sequence networks of a three-phase balanced star-connected load solidly grounded. The sequence network of a three-phase balanced star-connected load solidly grounded. So if you take this, this is the phase A, B, and C. So this is the impedance. Impedance of phase A is ZS, and impedance of phase B is similarly ZS. Impedance of phase C is ZS. This is the three-phase star-connected load solidly grounded without any impedance. So here, a three-phase star-connected load solidly grounded as shown in the figure. The sequence impedance networks are given as follows. Here, the sequence impedance is zero sequence networks equal to same VA naught is equal to IA naught. That is Z naught is equal to Z. Yes. So this is the reference bus. Here, the positive sequence network. This is the voltage between the just phases VA positive, and here the current is IA positive, and Z plus equal to Z. Yes. Next step, negative sequence network. Here it is VA negative, and here it is IA negative. That is Z negative is equal to Z. Yes. This is the zero, positive, and negative sequence of the three-phase star connected solidly grounded. So solidly grounded without any impedance. This is the sequence network. This is the sequence network as shown in the figure. Next, sequence networks of a three-phase balanced star connected load ungrounded. Ungrounded without grounded. What is the equation? What is the phasor diagram that we are going to see? That is a zero sequence network that we are going to see. A balanced star connected load ungrounded as shown in the figure. The sequence networks are given as given in the this figure. That is sequence zero sequence network equal to VA naught. That is current load bus. Current is like IA 0 because this is a zero sequence center. So the impedance Z not is equal to ZS, and here you see the reference bus zero sequence that is not grounded. So it is open here. Okay, not grounded. So similarly here the positive sequence network VA positive having the load current here IA positive, and here Z plus equal to ZS. So this is the reference bus. This is the reference bus. Next, this is the negative sequence network VA negative and having the negative impedance Z minus equal to ZS. This is the zero, positive, and negative sequence network of a three-phase star connected load and ground. Similarly, sequence network of a three-phase balance delta connected load. Delta connected load having this is the delta connection having the impedance ZS. This is the A phase, B phase, and C phase. This is the three-phase balance delta connected load. The sequence networks are given as here in the delta connected load. You see here BA not BA not. Here this is open because this is the delta connected. So zero sequence, there is no connection. So here Z not equal to ZS here, and here the positive sequence network, the positive sequence network, this is a VA positive, and here this is a Z positive is equal to ZS. This is the reference bus. Similarly, negative sequence network, this is a VA negative. This is the Z negative is equal to ZS having the some currents, that is a current is IA negative. Here this is a positive sequence. This is as IA positive. So here the zero sequence network, there is no zero sequence impedance because here you see there is no zero sequence impedance. So Z not equal to Z. So here it is open here. These are the zero positive and negative sequence network for this three-phase balance delta connected network with the load with the impedance ZS as mentioned here.